Welcome everyone. So people who are attending here in physically and also people who are attending through Zoom. So our speaker today is Professor Herbert Spohn. He's the emeritus professor at the Department of Mathematics at the Technical University Munich. Herbert has made profound contributions in the hydrodynamics of interacting particle systems and the studies of the KPZ universality class. And more recently, he has some remarkable results in the non-equilibrium transport using the nonlinear fluctuating hydrodynamics. His book on the large-scale dynamics of interacting particle system is an absolute benchmark textbook for many of us in the field. He's the recipient of the Daniel Heinemann Prize in 2011, Max Planck Prize in 2017, and in 2019, he got this very famous Boltzmann Medal Prize. He was also one of the invited speakers at the International Congress of Mathematics in 2010. So Herbert is visiting us for this week as the Sir Dorabji Tata Chair Professor. And today he will tell us his work on generalized Gibbs ensembles. So over to you.
Thank you very much. Now I guess you can hear me. Yeah. Okay. So thank you very much for this very kind introduction. And I just sort of recollecting, I remember that I was visiting the Tata Institute in 2006. And I'm very happy, that I have the opportunity to visit again. So let me sort of talk a little bit about the title first. So there was, I guess, 4 years ago, I attended a conference on cold atom physics, and people talked a lot about convergence to stationarity, equilibration, quantum quenches, and then there came this word GGE, the Generalized Gibbs ensemble. And so that was very interesting. I just listened, and but then I sort of at some point, they turned to me and asked, "What about classical systems?" Since they knew that I have been mostly working on non-quantum systems, either systems of classical mechanics or stochastic particle systems, which are also classical systems, right? And then I was a little bit surprised, and I tried to make up an answer, but I realized, there was basically nothing. I couldn't answer very well, and afterwards I sort of looked up the literature and just sort of nothing around. And I thought, that's a sort of, the question as such is sort of very interesting, and I wanted to sort of try to make some progress, and I'm sort of trying to tell you a little bit, what I and many others have been doing. Okay, and maybe I should give some explanations the way how I've organized the topic. There are many people who have working on this, mostly on quantum systems, but now also in classical system has become quite popular. And first I thought about some sort of review, but then I realized, it would be terribly boring. I tell you names which you maybe never have heard, and items which are unfamiliar. And so what I want to do is actually I want to sort of explain you. It's just the static part. This is why I put here the Gibbs ensembles in the title. So I want to tell you one little facet of a big program, and I just would like to sort of explain you why I'm excited about the topic, and I want to explain you what is actually really the problem. That's sort of the main part, and therefore you will find essentially no references, during my presentation. And but if you come to me, this can easily be supplied. Okay, so I just sort of wanted to say that it will not be sort of a big review. I just want to make sure that you understand what is actually the issue which we want to solve. And for that purpose, I have to start sort of a little bit more general than what is on the board, and sort of remind you, of a very successful theory, which is the hydrodynamics of fluids. Okay, so now if I talk about hydrodynamics, I always mean sort of on the Euler scale. Not even sort of putting transport coefficients and this, and then having sort of Navier-Stokes convection. I'm just thinking about the Euler scale. And of course, this was written down by Euler, many years ago. He had no atomistic model. He was just sort of, making sort of macroscopic arguments, but he figured out, what these equations would do. But then, once people understood that matter is made out of atoms, you can, of course, make simple models. I mean, so for instance, you take classical particles and they're just interacting by radial potential. And, then they just follow Newton's equation of motion. And, if the world is really of that microscopic structure, then, on large scales, I mean, you should see all these beautiful structures which you see when you actually look at real fluids. Okay. Now, the point is that, this is an early success of statistical mechanics. The point is that when you make a microscopic model, the validity of the hydrodynamic equations are sort of based on a very, very simple principle. I mean, you have many atoms like, the air in this room, and you look at a little fluid cell, and in this fluid cell, you will see in a very good approximation an equilibrium state. So it's just given by, the usual Gibbs-Boltzmann formula, but it has parameters in it. And the parameters, of course, is the density of particles. I mean, there's the energy of the particles, which is related to the temperature. And of course, a little fluid element can have a net velocity. So you have to put in, also the possibility that all particles together are moving with some joint sort of common velocity. Okay, so you have, in 3 dimensions, you have 5 parameters. And now the idea of hydrodynamics is that you have slow variation. I mean, you can look at this little fluid cell, and then you can look at some other fluid cell. And of course, there's no reason why the parameters in this cell should be sort of the same. Rather, they are changing in space-time. And so now, of course, you have to do some hand waving and sort of some figuring what kind of equations you get. But, at the end of the day, if you assume this local equilibrium, out of this, you will get the Euler equations. Now, what appears in the Euler equations is the pressure. That sort of determines, that's sort of the crucial sort of microscopic input. And it is the pressure as computed by the rules of statistical mechanics. That was a big success because, you have a continuum equation, which a priori, doesn't say much how matter, what is the internal structure of matter. But, once you have this sort of microscopic foundation, then you can make actually the relation to the atomistic structure. And it's only through the pressure as determined by statistical mechanics. Of course, for real fluids, maybe it's too complicated. You just have to measure the pressure experimentally. But still, I mean, in principle, it is really the pressure as computed by statistical mechanics. Okay, so now that's fine. I mean, this just works for ordinary fluids, but now they are sort of, very fine-tuned systems which have a very different structure. And, the Calogero fluid, which is sitting up there, is one of these examples. Namely, you have systems of classical mechanics which have many, many more conservation laws. They have conservation laws which are extensive. I mean, if I make the system large, I mean, then the number of conservation laws sort of basically goes with the number of particles. And then the question is, what happens to these hydrodynamic pictures if I'm in, such an exotic situation that I have this huge number of parameters? Can I still write down hydrodynamic equations? I mean, what is their structure? I mean, can I sort of, write them on a piece of paper? Can I put them on a computer? So that's really the question which I want to address during this talk. Okay. And of course, these are very fine-tuned systems. I mean, you cannot change the parameters. I will tell you what the Calogero fluid is. I mean, it's once and for all given. I cannot make little changes, then I will lose immediately all the conservation laws, right? I mean, so it's very fine-tuned, but within this framework, I mean, a very interesting, also probabilistically very interesting structure emerges. Okay, so that's sort of somehow the general business, and now I want to sort of so as I said, I mean, this sort of dynamical picture is just sort of at the moment in my mind, and I will not touch it in this talk. I will rather sort of, what for ordinary fluid would be computing the pressure, what is the analog for these integrable systems, and how do I, figure out what this quantity is. So it's really a static problem, which I'm going to discuss during the next sort of less than an hour. Okay, and so I will start with a very trivial example, which just sort of what you teach to your students, but it's just to make sure that everybody understands the terminology, and then we can sort of proceed sort of a somewhat more serious, oops, now this is not moving anymore. So you have to click your, Okay, so first I want to explain you, this notion of generalized Gibbs ensembles, which when I heard it, I had just a totally wrong sort of view of this. But now I can explain it to you here. So the point is that I will take sort of the most trivial thing which I can imagine. Namely, so these signs are not on my slides. I mean, but still they fit nicely to the slide. Anyway, so I'm looking at just sort of very elementary system. I have an ideal gas in one dimension. I do one dimension because I mean integrability works sort of only in one dimension. If I go to higher dimensions, I mean then we lose integrability, right? I mean, so all the time space is one dimension and time is one dimension anyhow. So, okay, so here I have my space-time picture. Now you start with some random initial condition. So here are the point particles. They have an intrinsic velocity and then just move along a straight line, right? I mean, and of course they move forever. It's infinitely extended, at least in my mind. I mean, so, I have some random initial position, some random initial velocity, and then I just let it move. Now, one very important case, of course, is the case of thermal equilibrium, which you teach your students. I mean, so then spatially you just take sort of a uniform distribution, or what probably is called the Poisson process. So you have points, and their mutual distances just have an exponential. The distance is exponentially distributed, and there's a parameter going with this density, which is this rho over here, and then so I put rho dx. I'm just saying that it's uniform, and there could be also an x dependence, but that's not what I want. I mean, this is not thermal equilibrium. Well, and then of course the velocities are independent IID, and the Maxwell distribution, the Gaussian distribution for the velocities, and you see that now I have two parameters. I mean the density and I have the beta, right? Okay, so that would be sort of what I do in thermal equilibrium. But now, of course, if you put an ideal gas sort of like in a little tube, I mean then typically it will be thermalized through collisions with the boundary, right? Because I mean the boundary has some room temperature, some other temperature, and then of course it thermalizes. But now I insist that the system should be truly isolated. There's just no interaction with the outside world, which in the lab maybe it's difficult, but mathematically it's very easy. I mean you just sort of consider the system and no coupling to any surrounding. And then it's somehow clear that the system will not thermalize. Now, what do you mean by this? Is that you see that there is no mechanism. So there's no mechanism how you could generate the Maxwellian, the Gaussian distribution. But on the other side, you do generate this Poissonian type of statistics for the particle positions. Now, how does this come about? I mean, so imagine that you start with initial condition, which in space are stationary, but they have some general statistics. I mean, not even any decay of correlations. I mean, just sort of imagine that but imagine that it's sort of statistically stationary in space, okay? And now I let them run, and now I want to look at some local observable, some function here, which is sort of, located near the origin, and I want to know what is its statistics after a very, very long time. Now, you see what happens is that after a very, very long time, if you sit here at the origin, what you're going to see are particles which are coming from regions which initially were very, very far apart because they have to move with the net velocity to reach the origin. But okay, so if I now assume a little bit of independence for large distances, you see that at later time, what I'm going to see is again, statistically independent. And so this will be essentially a Poissonian type of statistics. And so you see that despite the fact that the system does not thermalize, if I wait long enough, eventually it will reach a stationary state. And this stationary state, of course, is just exactly the same as up here. But the point is that there's simply no reason that you should have a particular velocity distribution. It's embodied into what you take as sort of initial statistics, right? I mean, the initial conditions sort of determine you for which kind of velocity distribution you're going to see. And I wrote it sort of so spatially it's Poisson, but and the velocities are still IID, but they have some velocity distribution, and I sort of write it in a statistical physics manner. I mean, I write this exponential of some potential, and I call this the confining potential. I mean, the name at the moment sort of looks a little bit strange, but you will see in a second that when I come to the more difficult model, I mean, then it really has sort of the effect of confining. I mean, basically what it means, it confines the velocities. You see, I don't want to have very large velocities. I want to have this function to be integrable, and so somehow there must be a mechanism in or sort of something in my system which tells me that you know I can normalize this velocity distribution. Okay, yes.
Are not confined in a box.
No, this is infinite. No, there's no box. I mean, for me, there will be never any. Well, I mean, at some point I will have a box, but at the moment, since it's such a simple system, I start immediately for the infinite system, but I have a finite density of particles, right?
You're just saying that the velocity is the same as that of the initial velocity.
Yeah, that's right. Basically, what I'm saying is, well, you still have to do that computation, but I'm just saying that in a rather simple way, the velocities which I'm going to see is embodied in the initial statistics. Yes.
By the stationary state in this case.
Well, it just doesn't change in time.
It's the same as the initial state.
No. Here I was thinking of a time-dependent situation. So I wait long enough, and then I'm saying in the long time limit, I go to something which becomes, it goes to something which doesn't change anymore in time. So it's only in the long time limit at the moment, right? Okay. And now I can ask myself, what is the statistics which are going to see at very, very long times? And the assertion is more or less independent of kind of, you know, what initial what kind of initial randomness I put into the system. I will see spatially a Poisson distribution with some density, where the density is encoded in the initial conditions, and with independent velocities. And you know, of course, and they cannot be Maxwellian. That's the whole point, right? They will have some velocity distribution, which is again encoded into my initial data. Okay, and so you see that if I want to now say what are the stationary states of the ideal gas, I need two parameters. One of them is the density, but then I also need this function W, this function V. I mean, so there is a function and a number which sort of characterizes what are the stationary states. Okay. All right. Now there's since also some people here from mathematics. I mean, there's a nice theorem which goes many years back to Calogero, and he sort of actually proved the theorem about this thing. And what you assume here is that you do this ideal gas dynamics, and then you ask yourself whether I can put particles initially in such a way that the statistics is stationary in space. So as I shift in space, I will see statistically the same, but also in time it's stationary. So when I move it in time, I will also see the same statistics. And then what he proves is that under very mild conditions, essentially optimal conditions, namely you just want to have a positive density, otherwise you have no particles. You want to have a finite second moment, finite kinetic energy. That's also a very natural condition. And the very important initial condition is that you want to have a finite entropy per length. I'm not going to write this down in any explicit way, but you see that the important point is that there could be since it's a mechanical system, there could be very singular initial conditions which you are simply not interested in, right? But and they are there, of course, and then somehow you have to sort of exclude them. And the condition of sufficient randomness sort of, is embodied in this thing. I mean, it should be a finite. If you remove this condition, then you can actually make counterexamples anyway. So you assume that, and then the proof of Calogero is that what you're going to see is, now of course, since I didn't assume any decay, it can be sort of a linear combination of GGEs. And what I mean by GGE is now this object here, right? I mean the density and the particular IID velocity distribution. Okay. All right. So this is sort of just to tell you, what this notion of GGE. So it's called generalized Gibbs ensemble. I mean, it might not be the sort of the most informative name, but somehow people introduce it and it's stuck. And so if you ask what are the GGEs of the Gibbs of the ideal gas, I mean, this is the answer, and that's sort of a theorem which tells you that there's in some sense nothing else than that. I mean, there are no other stationary measures which sort of could appear in the long time limit. All right, so now of course I've talked about the system with a rather trivial dynamics and also with a very trivial statistics, right? And now the rest of the time, I mean, I have to spend to convince you that this kind of picture persists. Of course, not in a totally trivial way, but persists when I actually put real interactions. Okay. All right. So now we come to this notion of integrability. Okay. So we have integrable systems now. The ideal gas is sort of integrable in a trivial way. I mean, you know, any some function of the momenta, of course, is conserved under the dynamics, right? I mean, that's this line over here, right? I mean, but of course, there's no interaction. You know, particles just move. And so, you know, as I said, I mean, it's an example which you tell your student, but you know, it's not so interesting. But now, yeah, I want to do something which has interactions, and so let me just do the most obvious thing. I mean, you know, you take a one-dimensional fluid. I mean, here you have the kinetic energy, and then you have a sort of mechanical potential which gives you the interaction between particles, right? And now you could ask yourself, whether for which potentials do I get sort of lots of conserved quantities, right? And so what I mean by conserved quantities is that, you know, they're sort of, I mean, I have here n particles, so I have functions on phase space in up to n, which are mutually, I mean, which they are mutual Poisson brackets. They are in involution, as people say. I mean, so their Poisson brackets, their mutual Poisson brackets is equal to 0. And the energy sort of, you know, in this notation has sort of the index 2. And therefore, you know, I can put m equal to 2. And so that means all these quantities are conserved, right? I mean, so that's the classical notion of integrability. There are some fine technical conditions which I want to sort of not mention here. It's not so important for me. But, okay, so the question is, you know, what are the solutions? And now, I mean, I put meta theorem. That's maybe not the correct terminology. It's sort of theorem which is not proof, but there's sort of a general expectation, you might call it. I mean, the information which we have is that we know, you know, certain models which have these properties, but only very few. And the only solutions which are sort of fall in this class are actually, you know, one can say it very easily. So I can put this interaction equal to 0, that was just the ideal gas. I mean, then there's a sort of rather trivial modification, but still quite instructive, is you mentioned that rather having the gas, I mean, you mentioned that you have hard rods. I mean, they are sort of moving like free particles, and then you do an elastic collision. I mean, that's sort of a rather simple situation, but it's still instructive. I mean, it's you know, still has a interesting nonlinear hydrodynamics. And then okay, so these I don't want to consider. And then there's sort of this famous work of Calogero, who discovered that if you put as potential exactly 1 over sin squared x, I mean, then you know, this system is integrable in that sense. Okay. So and then I put here plus, you know, there are many other models. I mean, you know, they're sort of generally referred to as Sutherland, Calogero, Moser. So Moser is the Moser from the Kolmogorov-Arnold-Moser theorem. I mean, he was very much interested in such kind of integrable systems. But you know, I'm not going to dwell on that at all, right? I mean, just really, I mean, this is what I promised at the beginning. The only model which I'm going to look at is the Calogero model, right? And I call it Calogero fluid. I mean, just to remember that, you know, it's a real honest fluid in the sense that you have, you know, an interaction between all pair of particles. Okay. No, do you some question or no? No. Okay.
So does the vanishing of Poisson bracket also imply that there will be local tensor?
Well, that's a good question. I mean, so in fact, I mean, you know, I put here yeah, I will come to that issue in a second. Yeah. Okay. All right. Now there are two limits which you can do. I mean, you can think of a high density limit. I mean, you know, then you know, at small distances, I mean, this function, since the sinh is linear, I mean, this goes like 1 over x squared. So you have sort of like a hard core, but, you know, with a very definite power law. And this model, you know, has been studied, you know, back in the 70s. I mean, in great detail, and it helped a lot in order to understand sort of more of the mathematical structure of the Calogero fluid. This both quantum mechanical and classical. I mean, that's a model for which you can get lots of explicit information, but I'm not going to touch upon this. And then there's another limit which you can do, that you do a very dilute limit. You see, I mean, these particles are actually, you know, it's a hard core. So once they never change, they can never cross, right? I mean, so if I give them 1, 2, 3, I mean, they will stay ordered in this way. Okay, and now you can say, okay, I mean, this is maybe too complicated. Let's simplify a little bit, and you see, I mean, this potential decays exponentially as I go for large distances. And so here I have a, let's say, a typical configuration. This is maybe the particle which I'm looking at, and then it interacts with its nearest neighbor and next nearest neighbor, etc. But you see, the next one is already sort of, in some sense, exponentially smaller than the one, at least, you know, if it's dilute, it's exponentially smaller than this one. And so one approximation is that you simply keep the interaction between nearest neighbors, right? And then you can write it down. I mean, so then this is approximated by the exponential function. And then you get a very famous Hamiltonian, which is sort of, you know, sort of the, I mean, the model which somehow on the classical side was the model which generated, you know, this business of looking at integrable many body systems. I mean, this is the famous Toda lattice, which are sort of classical particles which are interacting with an exponential potential. But you know, this is a lattice model. You know, I have a J and I have to label particles, and then you get, like in this picture, only, you know, interaction between sort of nearest neighbor. I mean, not in terms of order. I mean, there's no ordering here anymore, but in terms of the label. Okay. The Toda lattice is also a system which we understand very well, but I mean, you know, as I promised, I will not make any detours. I just want to look at the Calogero case. Okay. Okay, so now I've introduced for you the model, and now the next thing is, I mean, how do you see that this model has a, you know, we have n particles. I mean, at the moment it's just n particles moving on the real line. I mean, how do I know that I have so many conservation laws? Okay, and the answer is that you know, that again, this is something which goes back to the early 70s. The answer is that sort of in the classical context, the most powerful tool is what people call a Lax matrix. Okay, so I have to explain to you what this Lax matrix is. So you define a Lax matrix. So here's the definition. I mean, this is an n by n matrix at the moment, right? Because we have n particles. And what you do in this matrix, I mean, you just insert along the diagonal the momenta, right? I mean, so that's the diagonal piece. And then there's an I here, which at the time was sort of a big surprise because people try to find Lax matrices which are real, but that doesn't work. I mean, so you put an I here, and then here you basically put the square root of the potential. I mean, so you know the potential was 1 over sinh squared, and now I put the 1 over sinh. Okay, and now you see it's a fully occupied matrix, but when the indices I and j are far apart, I mean, then, you know, because of the sinh, I mean, you know, they are sort of decaying. So you should think of it as almost sort of like a tridiagonal matrix. I mean, you know, it's really a band matrix, but then of course you have tails, which somehow you have to sort of include if you want to have this integrability. Anyway, so that's addition of this matrix. And then there's sort of, you know, it's called Lax pair because there's yet another matrix, which I'm not going to write down. But the crucial point is that, you know, so this Lax matrix is a function of all the P and Qs, right? So I can evolve this Lax matrix in time. So I just look at the same matrix, but now I insert the configuration at time t. Now, once I do that, yeah, I can look. So there's now a t dependence, which I didn't explicitly indicate. But now you can look at the time derivative of L. And the miracle, I mean, it's really a miracle, and it's sort of very, very much related to the miracle of integrability, is that this derivative can be written as a commutator. Okay, with some matrix, it's not so important. I mean, so it's just the main point is it can be written as a commutator. Okay, you see, if I take any, of course, you know, if I take some other potential, of course, I can do the same construction. But this certainly will not be true. I mean, there's just no reason when I sort of evolved this according to Newton's equation. I mean, this can be written as a commutator. Okay, so that's the sort of the core basis of classical integrable system, that you have a Lax matrix at your disposal. Now, why is it so important? Because you know, so first of all, you see that it's a symmetric matrix. I mean, because you know this is odd, and so here I have the I, and so you can look at the eigenvalues. And, you know, you can, for instance, look at the time evolution of the, I mean, I will do this in a second anyhow. Let's say I take the nth power of that, I take the nth power of this matrix, and then I take the trace, and then I take the time derivative. And then, you know, when you look at this commutator, then you realize that this time derivative actually vanishes. And therefore, the conclusion is that the eigenvalues of the Lax matrix are not changing in time. You have n eigenvalues, and therefore you have n conserved quantities. Yes?
Perception why The dimension of n is the Lie bracket, and can one interpret as a Lie bracket?
Yeah, there is sort of something which, yeah, that's a nice remark. I mean, there's a whole theory which is sort of related to Lie brackets, and you know, in this framework, there are many other models which you can. It's an interesting direction, right? Because you get other models, but I mean, for me, this Lie bracket structure is not so important. Okay, now the main point. I mean, this is what was the question. You know, the main point is that the eigenvalues are not local. I mean, if I change a little bit, you know, I take this matrix, I forget about time. I mean, you know, this is sort of the last time. Now it's completely static. I want to study this matrix here. Now, if you start changing a little bit the Q, I mean, the eigenvalues will sort of change all over the place, right? I mean, so these are non-local functions. But when you take so what I mean by non-local, maybe I should explain this a little bit. I mean, you see, if I take the sum from j equal 1 up to n, this is what we call a local function, because, you know, I just, you know, the p sort of are just sort of you know, in terms of these indices, it cannot be more local than that, right? It has, this object has a density, you know, when I think relative to the as lattice sort of, you know, the pj, which just depends on one single lattice side. Now you can take the square of that. And that's, of course, also not changing in time, yeah? Because if the sum over p's is not changing in time, then also the square of it is not changing in time. And then, but this is a highly non-local function. And in hydrodynamics, you know, this is not what you want. I mean, the hydrodynamics relies on the fact that your conservation laws have a density. I mean, of course, you know, the conservation laws are extensive. I mean, so, you know, they are proportional to n if you want. So if you think in terms of system size, but what you want to have is something that they have a density, and that density is local. It's just like, you know, when you usually write down sort of, you know, Hamiltonians with short range interactions, right? I mean, then you write some density. Of course, you do the sum over j, but the main point of this is that, you know, when you write down the Hamiltonian, but the main point is that the energy density is something which is sort of local, right? So local means not necessarily, you know, exactly at one side. It could be at 20 sides or something like that. All right. Okay, so now let's first sort of think of this for a little bit. I mean, so you see, I mean, in order to make objects which are local, I mean, then the point is that the correct local conservation laws are the traces of L to the n. This you see, that's sort of, it's that quantity which is local. Now, of course, it's not local because I take the trace, but the trace is sort of, you know, is the sum over the diagonal elements. And so the density of, you know, the trace L to the n is proportional. So L, maybe, unfortunately, there are two n's. I mean, there's a little n, which is this power, and then there's sort of n, which is the number of particles. I mean, so what I mean here is that this quantity, you know, I'm still looking at n particles, you know, it's a sum over the diagonal elements, and therefore this is sort of proportional to n. But the density, you know, L to the power n, jj, this is something which is local in that sense. Because, you know, when you work out this trace, I mean, you just take, you know, L times the same, the same matrix, and then since, you know, your matrix element have to start at j and they have to end up at j, I mean, you cannot go too far away from j, right? I mean, so this is, I mean, you can end sides away from j, but you will not pick up any further terms outside of that. So this is really something which is local. So it's those quantity which you have in your hydrodynamics theory. Okay, and so now you can write down easily the densities. I mean, this is sort of what you do in the classical case. I mean, you know, we are still working on we are on the continuum. I mean, so you just want to have that the particle j is at the position x. I mean, that's sort of because I'm writing the density now of my conserved field, and then you have to weight it with this thing. I mean, you know, usually you put here the pj or maybe the energy, but now we have more conserved quantity. So I just take, you know, this very particular matrix elements of the nth power of the matrix, right? All right, and this gives me now you know, I do the sum over all particles, and I mean this index n can run from 1 up to the maximum number, and there you see that these are sort of the densities of my conserved quantities. Okay, and now you see, if you do the algebra, it just works out. I mean, this is q of x. If I do the integral, which sort of, you know, I just omit this x argument, this means that here it's written. I mean, I do this integral, and then you see that I do work out the delta function, which just gives me 1, and then of course I see the trace to the L. So that's the global quantity. This is sort of like a Hamiltonian, right? And then, yes. Well, I mean, this you see, I'm trying to say that this I mean, just work out, you know, what this object is, and then you see that there will be never an index appearing which is more than n sides away from the JJ. Okay, so you just have to do this matrix product, right? Okay, so now let's see whether this sort of makes sense physically. Well, I mean, let's first look at n equal to 0. I mean, that is well, you know, then it's just a trivial, you know, sort of the unit matrix, but you know, this just sums up to n. I mean, so this would be the particle number. If I take Q1, which is the first power, that's just the sum over the diagonal. Now in the diagonal, I put the momenta, so that's the total momentum, so that's fine. Now I look at the energy, and presumably it's L squared. Why is it L squared? Well, because you see, else, I mean, if I square the matrix, then I have to take the sum over the square of all matrix elements, right? And so if I take them along the diagonal, I mean, those matrix elements were Pj, and then if I square them, I get, you know, I mean, except for the factor 1/2, I get Pj squared. And the off diagonal was the square root of the potential. And so if I sum the off diagonal elements, I get the full energy. So the Q2, except for the vector 1/2, is really the energy. And of course, then the higher orders, I mean, it goes up to n. Of course, they have no physical name because, you know, they're not so, you know, I mean, the ones which are most interested in are this low order quantities. But if you want to do the GGE, I mean, we have to keep all of them, right? I mean, that's because, you know, in the dynamical picture, all these fields somehow will couple with each other. And so you cannot just sort of start, okay, let's look only at one or two of them, right? I mean, all right. So now we have the conserved quantities. And now comes the GGE, right? I mean, so now we have to do what you do in ordinary statistical mechanics. We have to somehow, you know, we cannot work on infinite line, and we have to fix some finite volume. So let's put the particle on the ring. So like I put over here. But now you see that you know, of course we don't have any long range action, but still we have this exponential decay, right? And so what is the interaction on the ring? Well, you know, that's this sort of image charges. You see, I have the ring, but now you have to, you know, include all the image charges. And basically this means that you know, whenever I have some function f, let's say, you know, with real values in the full line, I mean, then I periodize. So it must be a function which has some decay, but then I periodize it through this sum, right? I mean, so if I do this periodizing operation, I mean, this is called here L. So I fix first the volume, you know, size of the ring, which is L, and then I sum, and then I get the periodized function, which I indicate by this index L, right? And so you can do all of these things. You see, you periodize your original Calogero-Sutherland, the Calogero-Hamiltonian, you periodize your Lex matrix, and then of course you still get the system, you know, because it's just sort of a simple linear operation. All the sort of identities which I wrote down are still correct. So you are assured that even if I put the systems on the ring, it will be still integrable, right? Just according to the same construction. Now, you know, some of these objects you can actually compute explicitly. I mean, so if I take the periodized 1 over sin squared, this gives you the double periodic Weierstrass function. It's not so important. It's just sort of fact that, you know, you sort of, you know, you get sort of a function which is tabulated, which is very well known and very well studied, right? Okay, so now I put an index L. I mean, just to remind myself that everything is sort of on the ring. Okay, so now comes sort of the most important part of the talk to some extent is that now I want to write down what is my Gibbs distribution, right? But now you see I have now n conserved quantities, and if you look in the book of Gibbs or, you know, any good book on statistical mechanics, it's clear what you should do. At least sort of if you work in sort of like a canonical picture, you should simply take these conserved quantities and put them up in the exponential. It's e to the minus beta h. right? I mean, and then if I put the particle number, it's e to the minus beta h plus mu n. And if I have now something else, I just also put it in the exponential. So the generalized Gibbs just says that, you know, whatever conserved quantities you have, I mean, they have to be locally conserved, but, you know, this we sort of ensured. I just put them up in the exponential and sort of, you know, it's a linear combination. So I call this sort of something like, my chemical potentials, and then I get, this is the formula, sort of what people usually write down, what they mean by generalized Gibbs, right? I mean, so you have, now you see that eventually, you know, n will go to infinity, so you have an infinite sum, and you have sort of, you know, a large number of chemical potentials. Okay, and now I want to do one thing. I mean, I wanted to write on the board so that you can see that. So you know, this notation is a little bit inconvenient. I mean, so I want to write v of x, not just given by this power series. I mean, I don't know. I summed from 0 here, 0 up to infinity, mu n. So these are my given chemical potential x to the power n, right? I mean, it's just a power series. And now you see that if I introduce this. Okay, so if I introduce this confining potential, I mean, I call this the confining potential V. Then you know, the next part in my formula is the next part in my formula is, you know, if I just, you know, diagonal, you know, sort of use the diagonal representation, and you look at this quantity here, then you see that it's nothing else than the trace of some function of our Lax matrix periodized, right? Now, you know, just sort of, you know, this quantity, I mean, this quantity here, the Qn to the L in the diagonal representation, maybe I should write this down also again. I mean, so the Qn, of course, in the diagonal representation is, you know, it's just the summation j equal 1 up to n, and then I have here just the eigenvalues lambda j to the power little n, right? I mean, so this is why you get these identities, okay? And this is now much better because you see now I'm already in the situation that you know, the generalized Gibbs measure is sort of defined through a function. Of course, you know, if I take a very simple function, I mean, if I just take, you know, the quadratic function, then this will be thermal equilibrium because, you know, it's just x squared and that's trace L squared and that's just thermal equilibrium. But then I could take a quartic, but, you know, there's no reason to think about polynomials. I mean, you know, it's just sort of some function which is confining. It just has to go up, just like we had for the ideal gas. Yes?
Does it have any number of intensive conjugate?
Yeah, that's right. Yeah. But that's just a sort of. No. It's just you know, at the moment, it's just okay. What I'm trying to emphasize is that our generalized Gibbs measures will depend on the density, which I'm going to discuss in a second, and on, you know, if I write it like in the first formula, like here in this formula, like an infinite set of chemical potentials, right? I mean, you know, they don't have any sort of immediate sort of physical meaning, right? I mean, but that's simply what the generalized Gibbs measure is, right? And I'm just trying to say that rather than thinking sort of in terms of this sort of discrete sequence of numbers, it's actually, you know, when you do this little computation with the eigenvalues, it's actually much simpler to think about this object here, right?
My question was, if we were thinking of finite number of conserved quantities,
yes.
One also consider the constant pressure ensemble, you would have e to the minus PV.
Yes.
Now, P would be same everywhere in the system.
Yeah.
Half of the system is in equilibrium with the rest of the half. So the sense of local equilibrium of this pressure.
Yeah. Well.
So in this case, is there any such analog?
Yeah, you know, but I'm at the moment, if you want to, I'm just starting, so to speak, what would be the distribution in one single cell, right? I mean, so I'm always sort of, yeah. Okay, so let's see, what did I want to say here? Yes, okay, so it's this formula here, right? And now, of course, the a priori is the usual 1 over n factorial, the dq dpn. And of course, now you see that the confining sort of makes sure that of course the dq is okay. I mean, that's sort of on the wing, but the dp, you know, when I look at at these objects, then there must be a mechanism that this dp integral actually exists, and then this sort of comes because I'm assuming that the v is confining, just as I had at the beginning, is a potential which simply goes up, right, for large values. And so when I put in the exponential, I make sure that eigenvalues which are very, very large, get a very, very small weight, right? I mean, it's confining in a sort of conserved, what people call in the spectral parameter. I mean, so it's confining the eigenvalues, if you want. So, okay, so now let's see. Okay, so now we have to look at a second at the parameters. I mean, so we have the volume L, we have the number n, so there will be a density, and we have the confining potential. And I put here fixed, but what I mean is, just like these are intensive quantities. So V is given once and for all. It does not depend on the size of the system, not on L and not on the number of particles. It's given once and for all, just like the chemical potential for the particle number, right? I mean, beta is also a parameter which is not, I mean, the inverse temperature is a parameter which does not depend, I mean, in the statistical equilibrium statistical mechanics setup, it does not depend on the volume or the number of particles you're looking at. Okay, so now I hope I made this central notion clear. I mean, so we were working here from the beginning sort of in a canonical. I mean, you can also think of microcanonical things, but that's sort of more cumbersome and in fact not really understood, but that's what I'm doing. Okay, so now let's see what we here. Okay, so now maybe I have to explain you what the goal of the whole enterprise, so to speak, is. I mean, so of course we want to take the infinite volume limit. So here I take parameter nu, which is sort of the inverse of the density. So it's length divided by the number of particles. Here there's an n missing, so it's 1 over n. And the first thing what you want to do is maybe compute the partition function, which would be the 1 over n nu, and then the log of this object which I told you, and then of course this ratio. I mean, the nu is again fixed, right? And then I will get some free energy which depends on a number which is nu, I mean the free volume, and on the confining potential, right? So it will be a functional of the confining potential, right? You see, for ordinary statistical mechanics, we would have the free energy as a function of 2 or 3 parameters, but here it's a function. It's a functional of the confining potential. Okay, it's a more complicated object, right? Okay, now what do we want to know? Well, at free energy, yes, but you see that there's another thing which we actually really want to know, namely, you see, we want to somehow get a quantity which encodes the average values of the conserved fields, and that's something which is very well known in theory of random matrices. This is what people call the density of states. So the real thing which we would like to get is the density of states of the Lax matrix. Okay, so you see, and that's of course defined in the obvious way. You have an n by n matrix. I mean, it has these eigenvalues lambda 1 up to lambda n, and then you put, I mean, what people call the empirical density. You see, I mean, the lambdas are of course random because they are the eigenvalues of a random matrix. But now you want to look at and they are very sensitive to whatever microscopic configuration I have. But if you now take this density, the density as such is sort of something which is about the robust, and so this is simply the definition of what people usually call the density of states, right? I mean, it's just a matrix, and then I'm plotting the eigenvalues and I normalize them to 1. So that's something which is normalized to 1, right? If I do the integral over W, I have the 1 over n here. This is just equal to 1. Right? So it's actually it's a random normalized probability measure, right? And now what you really would like to prove is that in the large n limit, this density of states, which is random, goes to a deterministic limit, right? I mean, so it's really a law of large numbers. I mean, this object, of course, the lambdas are fluctuating. This object is fluctuating. And therefore, you expect that there should be sort of like a law of large numbers. Okay, so let me don't say much about the other things. I mean, so this is really what you would like to get. Now, why is this important for the hydrodynamics? Maybe I don't. Where's our? Okay, so I have to look. How long do I go until 30, or a little bit more, or? Okay, okay. So we'll see. Okay. Yeah, no, I don't want it to take it. Okay. Okay, so why is this important for thermodynamics? You see now, I mean, if I have the density of states, I mean, sort of the picture is the following. So I take this Calogero fluid, you know, with huge number of particles, and now I look at a little cell. And this little cell, and let's say I can observe, you know, the position momenta of the particles. I mean, they're just random, and you don't see any structure whatsoever. And I look at some moment later, it will be some other end random configurations. So this is, you know, totally uninformative. However, if I do some clever trick, namely if I use my Lax matrix, so to speak, as a microscope, which of course numerically I can do very easily. I look at this little cell, maybe I have 1,000 particles there. You know, I record their position in momenta. I compute the eigenvalues of the Lax matrix numerically, let's say. Okay, that's fine. So I will see some, you know, some function with some bumps or so. And now I go a little bit later and I do the same thing at the time evolved configuration. Then I will see again a Lax matrix, but, you know, it's sort of closely related to what I have seen before, you know, because it's a conserved, you know, conserved field. It doesn't widely change back and forth, but it sort of evolves very smoothly. And so you have a chance that, you know, it actually satisfies the differential equation. You see, when I have all this sort of chaotic noisy thing, I mean, then it's not clear what kind of equation I should write down. But once I look at that, you know, a cell and the corresponding Lax matrix, the eigenvalue of the Lax matrix, these are the slowly varying fields. All right. So now let's see what we can do. Okay, so now, okay, so now, let's see, maybe I should go back. Okay, so what I want to do now I want to, so basically I'm now concentrating, you know, I'm not saying anything more about the density of states, but I want to concentrate on the free energy. And so I want to explain you how one actually can compute the free energy. So that's sort of, I mean, there's more on my slides, but maybe I will then just simply stop, right? I mean, that's sort of the usual thing, but it's better if I explain slowly rather than sort of trying to look at the end. I mean, okay, so the question is, so here I've written down, you know, what the problem actually is, right? I mean, so now, okay, so I guess what I want to say is that if you put the particles on the wing, and of course you can write down, you know, what is the partition function, but, you know, then you take a cup of coffee. I mean, that's it, right? I mean, nobody knows what to do with that formula, right? It's just too complicated. I mean, and nobody had any good ideas so far. Okay, so now I'm proposing sort of a slightly different approach, and you will see that with this slightly different approach, actually, I will tell you at the end of the argument, I will tell you what is the free energy. Okay, but the computation on the wing, you know, I'm not saying that it cannot be done, but I mean, just nobody was able to say anything sort of clever. Okay. All right. So let's try to do that. And so I'm doing something which, of course, you learn in your class. I mean, you confine your system. So now I put here an external potential, and you know, the hope would be that, you know, whether I put it on a wing or whether I put it in an external potential, you know, it doesn't make any difference, right? Oh yeah, sure. It will definitely break integrability, but now I'm just doing statistical mechanics. You see, I mean, I just want to compute the free energy. Okay, I mean, I will not. You know, I'm just, you know, it's basically saying that. So I have written down for you what is the free energy on the wing. I mean, of course, when I do the dynamics on the wing, that is still integrable, right? And I'm just telling you, forget about the dynamics. I just want to compute the free energy. And then, you know, I do what everybody else does, right? I mean, you know, you put a wall. I mean, you know, which, you know, right? I mean, you don't worry anymore about the conservation laws. I mean, because you're not looking at the dynamical problem, right? You just want to know what the free energy is in inch and volume limit, right? And so I'm just trying to say that you know, I mean, this, and presumably this you might be even able to prove that you know. Whether I take here this on the wing or whether I put a confining potential, you know, the large end limit should give simply the same result. I mean, nobody has proved it, but I mean, that sort of looks like something one might be actually to do. Okay, and so now I have this external potential, which at the moment is sort of somewhat arbitrary, right? I mean, it's free choice. Now you see, you know, I would like to go to, you know, I would like to go to new coordinates somehow. Oh, well, let's do this later. Okay, so this is what I want to do. Okay, yeah. Okay, now you know this doesn't make the problem any simpler because yeah, but okay, so maybe I put it this way. I mean, you will see in a second that I make. I mean, this comes then on the next slide. I mean, you know, I will make a special choice of this external potential. But anyway, I mean, this is sort of roughly what this external potential looks like. And now it's a new technique which sort of is you know, I mean, of course somehow in spirit, I mean, maybe around, but you know, to actually use this to prove theorems, I mean, that's sort of really a new result. But in any case, I mean, so what I want to do is I want to sort of instead of using the P and Q, I want to use scattering coordinates, right? So now I'm thinking of n particles still on the real line, but without any external potential. And I just want to use this in order to use sort of convenient coordinates by which I can compute this complicated partition function. Okay, and now let me show you what they are. I mean, so now I have n particles just on the line, and I'm looking at the long time limit of the momenta. Now you see, when I take the long time limit, I mean, these particles, because it's a repulsive potential, they will separate. So this means the distance becomes huge, and the off-diagonal elements of your Lax matrix will go to 0. So then, you know, the Lax matrix becomes diagonal, and everybody can sort of, you know, find out the eigenvalues of a diagonal matrix. And these are just the momenta, the asymptotic momenta. So these are just, I mean, the eigenvalues must agree with the asymptotic momenta. That's what I'm trying to say. I mean, so in the long time limit, you know, these particles will move with constant velocities, but you know, because by construction they must agree with the eigenvalues of the Lax matrix. So in the long time limit, you know, your dynamic sort of diagonalizes the Lax matrix. Okay? But then there will be a first order correction, and the first order correction I can see when I look at the positions. I mean, so that's the Qj at time t. Now I've subtracted here the asymptotic limit, and the assertion is that, you know, there will be still some non-trivial limit, which I call here phi j, which is some number in R. Okay, so these are the scattering shifts. I mean, so you know, you don't follow exactly, you know, just a linear trajectory, but you know, you have an order 1 which sort of shifts you relative to the trajectory. Okay. All right, but now you see the amazing thing about this thing is, because it comes from scattering theory, that, you know, so the lambdas and the phis are some complicated functions of the initial conditions. But the point is that you know, when I look at this map, I mean, which sort of relates these two coordinates. I mean, so the lambda and phi are sort of the scattering coordinates, and the p and q are the original mechanical coordinates. This is actually a map which is 1-to-1 and which is canonical. And so this means, and that's sort of, you know, the clue of the whole thing. This means that if I look at this volume element, it's not, you know, the volume element dq dp is equal to the volume element d lambda d phi, because it's a canonical transformation. All right. Now the picture which you should have in mind is sort of something like this. I mean, so you know, you go. I mean, you have some complicated. So this is space-time. So you have some complicated interaction for short times. I mean, you don't really want to follow. But when you look at very long times, I mean, then I'm saying that, you know, that these particles are sort of have these outgoing velocities, and here, you know, maybe I can label them in their order 1, 2, 3, 4. But for the incoming situation, it's the same thing, right? If I go backwards in time, you know, they also separate, and you know, again, there must be the eigenvalues. And now the miracle of integrable systems is that, you know, it's like what you know as the Newton cradle. I mean, you know, when you ever go to some bookshop or so, you know, they have these balls hanging, you know, as a cradle, and then you sort of move them, and you see they do exactly this thing because it's an integrable system. The point is that you know, so these are now sort of the quasi particles. I mean, so the point is that you know, the incoming configuration is simply the reverse as the incoming momenta is simply the reverse of the outgoing momenta. You see, if I would take a non-integrable system, I mean, this picture with repulsive potential, this picture is still true, But the point is that you will not have such a simple relation between incoming and outgoing. It's only for the special case of the Calogero, I mean, you get this incoming and outgoing. And then, well, I mean, now you can say, that's very beautiful. Now you see your new coordinates are the eigenvalues. So now, of course, this trace becomes simply the sum over, because now L is a diagonal matrix. I mean, so this becomes now really like an external potential. It's very nice, right? Here's the lambda d phi, which is sort of these new coordinates. But now you see the external potential will become a horrible mess, because this depends on lambda and phi, and who knows what it is, right? But this is a correct identity. I mean, that's just no question that this. And at the moment, I'm so again, you have to integrate over all. I mean, here you integrate it sort of just over time ordered positions, or spatially ordered positions. Same thing over here. I mean, so you ordered the eigenvalues are ordered lambda 1 less than lambda 2, etc. So you integrate over. So the phi n integration is over Rn, and this are over ordered n tuples. All right. So you see, it's a nice idea, but doesn't go so far. And now the amazing discovery, or I mean, sort of, at least to me, amazing discovery is that that there's a very special choice of this external potential, which allows you to actually, in some sense, sort of close the computation. Namely, if I decide to take as an external potential this very particular function, so it's a cosh of x, I mean, so this is something which goes up, but now I put a very, very small prefactor, and when you look at the formula, you see that this is the correct prefactor, and then the external potential sort of looks more or less what I have shown you. You see, in the middle, it's sort of essentially 0, but then when I go to L, I mean, then it sort of shoots up exponentially. So that's a very good confining potential. Okay. Now, the claim is that in this case, there is a simple formula for this transformation. And after going to the new coordinates, you get a sum over J. You get certain coefficients here, but which do not depend on the shift variables. They depend only on the eigenvalues. And then I here have the cosh of phi J. And now you see that if I put this in my partition function, it's just like an external potential, so I can integrate over the phi's. Of course, the yj's are still there. Anyway, so let's do this. I mean, the yj have this particular form. And now if I have done this integration, you end up with this expression. So the phi integration has been done. It's symmetric in the lambda, so I put a 1 over n factorial. Then this is the confining potential, which now really confines, the lambda integrations. I mean, if I would not have this factor, then I would see infinity. But if I do this factor here, then it's a confining potential. And then you integrate over this cosh. This gives you a modified Bessel function, which looks something like this. It's sort of exponentially for large distances, and it goes like minus log x near the origin. Okay, now I'm already over time. So maybe I stop sort of after that slide. Maybe I just stop, right? I mean, so. Okay, now up to you. I mean, but I don't want to bore the audience too much, right? I mean, so okay. Anyway, so let me sort of just finish this, and then maybe we can discuss whether. Okay, so okay, so okay, so now okay. Okay, so you see, what is the point? I mean, you see, for finite n, I have now, if I do this particular confining potential, I have a somewhat complicated formula, but it gives you the full distribution of the eigenvalues. So you have a random matrix, there was this Lax matrix, and now now you want to compute, let's say, the distribution of eigenvalues. That's usually a very difficult thing, right? I mean, of course, for some cases, the whole random matrix is full of this. I mean, they know how to do that, but in very particular cases, I mean, like GUI, or you have sort of course, it's a well-developed field. I mean, Meta is a pioneer on that, right? I mean, but here's sort of another matrix which is not not fully occupied. I mean, it's more like a tridiagonal matrix, and by some miracle, because of integrability, I can actually tell you exactly what is the full distribution of eigenvalues, right? I mean, it's just this object which is sitting here under the integral. Okay. Now you still have to do the large n limit. Right? Now, now you stare at this, and if you stare sort of, I mean, you have no chance, right? I mean, you can just stare at this for a few seconds. You might think, I just sort of, I'm stuck because there's another difficult problem. But now there comes this great miracle that when you look at the dependence on the white J, I mean, of course it's a little bit hidden, and I cannot do it more clearly, but I can tell you the point is that this distribution depends only on the density of states or some functions of the density of states, but it's not something more complicated. Okay, so so maybe people can ask me later on. I mean, what I mean exactly. So in a statistical mechanics language, is that despite this thing sort of looking very complicated, it's actually a mean field problem. Okay, now those people who know what mean field is, maybe they understand, but I'm sort of running out of time to really explain this. But the point is that it's really a mean field problem, and the crucial quantity is the log of the white J. Now the log of the white J, you see, is sort of, you can see this, and in the continuum, this quantity here is simply the density of states integrated against this logarithm. And now the very surprising thing in all these integrable systems, when you work with the free energy, then at some point you discover that your free energy functional will depend on the two-particle scattering shift. And this is sort of what happens in this step. You see, when I look at two particles Calogero, so these are just two particles. Here I plotted these two particles. And I just solve, for the relative motion. I mean, you can solve this explicitly, right? It's a two-particle problem, but we have, it just depends on differences, so I can reduce it to a one-particle problem. And if you solve this, I mean, the solution looks like this. I mean, it's just like, as I told you, for n particles, but now you get an explicit computation. It has asymptotically goes along the line. Here, of course, is the eigenvalue λ1, I mean, which is the same over here as the eigenvalue λ2, which is over here. And when you do the computation for the specific Calogero model, then you see that the shift, which I'm going to see here, depends only on the difference of the two incoming momenta, as it has to be, but it's that very particular function. But you see, if I take the log of yj, it's that particular function integrated over the density of states, which I'm going to see. So, this is sort of, I have to take the log, then this becomes the sum, and in the limit, it becomes an integral. So the point is that I'm writing down for you in a second the free energy function. The free energy function, in all these integrable systems, surprisingly enough, you get a free energy function, and this free energy function, its main ingredient is actually, the two-particle scattering shift. So somehow, in this free energy, some dynamical quantity appears. And that's true for all integrable models. I mean, the delta Bose gas is a famous paper of Yang and Yang, who discovered this kind of relationship. And then there are many other papers later on, I mean, which sort of, it seems to be a totally generic thing. So that's the last thing which I sort of want to make sure that I can show you, is that now you do the asymptotics of this. And the assertion is that what you find is that the free energy is the solution of a variational problem, but of a variational problem which involves just the density of states. So it's just a variation over densities on the real line, okay, which are normalized to one. And this has sort of a rather familiar structure. So let me just show you this density function. I mean, so here it's the function which I get just from the external potential. That's sort of clear that it's just linear in the density. Here you see the rho log rho term. I mean, that's the entropy term that comes from the Lebesgue measure. I mean, the integration over d lambda basically produces for you the log. And then you get some somewhat unpleasant sort of nonlinearity, which is sort of the log of 1 plus. And you see here, you see the density of states and then integrate it against this two-particle scattering shift. Okay? And then the assertion is that, you have to look at the minimizer of this variational problem. And if you evaluate the f at the minimizer, then you get really the free energy. And then you sort of work a little bit harder, and then you figure out that the minimizer of that function is actually the density of states. So you see, I've produced for you a formula which gives you actually, that what you hope get to the density of states. And that's very unusual because, when you just take, sort of essentially sort of tridiagonal matrices, Jacobi matrices, and you want to, you put the entry sort of like random, maybe IID random. I mean, I have no idea how to compute the density of states, right? Here for that very particular model, you can actually write down a variational principle, right? Now, once you have a variational principle, you can use the computer and actually solve it, and you will find how this works for the density of states. Okay, now I'm really, yes, okay. Well, because I mean, this is what I was trying to say in sort of very vaguely, but it's hidden in this formula. It's a mean field problem. Whenever you take an Ising model, mean field, I mean, then the way how to solve it is that you realize that the free energy just depends on the magnetization, right? And it's the same thing, but only in infinite dimension. It's just exactly the same. It's of course more complicated, but I have to do a little bit asymptotics of these K0 functions, things like that. But that's how it works. Yeah. Okay, so now let me really stop here, I think. But before stopping, I want to show you. So I skipped some things which are not so important. I just want to show you some numerical simulations which are actually done for the TODA, but we are doing now things also for the Calogero and the pictures presumably will look sort of rather similar. I just want to give you some understanding that I mean, you might think that maybe it's sort of nice mathematics or some interesting mathematical structure, but it has also predictive value. I mean, this is just want to get across. And so what we do in this picture is that what you do in many statistical mechanics problems. I mean, you just want to look, let's say, at the momentum, I mean, space-time momentum correlation function, right? Now, the point is that this space-time momentum correlation function, you can sort of, I mean, you have to do some numerical things, but you can write on a rather closed formula using this whole machinery. So there are still many steps in between. So I will not display any formula, but I just wanted to show you that there's a formula which you can put on a computer, and with computer precision gives you a theoretical prediction of what these functions should look like. You see, these correlation functions look very unusual. I mean, they are sort of, I mean, they scale ballistically. I mean, so when I look at, I mean, this is at various times here, but well, I don't know. I think this is a fixed time. So this is time 600, and we have sort of like 4,000 particles. And I'm just computing here. I guess here it's the momentum, and the energy. I mean, I compute these correlation functions, and so you have, they're correlated over large distances. I mean, because it's a ballistic system, and so things sort of simply spread out ballistically, right? I mean, so, but now you want to really know what these functions are, right? And the scheme which was trying to give you a little bit sort of like an aspect actually gives you a prescription, gives you a theoretical prediction of what these functions should be. Okay, now you go ahead and do a molecular dynamic simulation. This is what we have done over here. I mean, you take sort of in an approximation, but just imagine that I solve numerically the equations of the Calogero fluid. And I take an initial distribution. I mean, these are always thermal. Initial distributions are just thermal. So you take the usual e to the minus beta h. I mean, you throw out your 4,000 particles according to this statistics, and then you evolve it for 600 time steps, and then you average over 1 million or maybe 5 million or 10 million in order to get smooth data, and then you can compare. And then the dotted lines are the ones from the theory, and the colored lines are the ones from the molecular dynamic simulations. And what you see that there's absolutely amazing agreement. There's no free parameter. I mean, we just sort of put it one onto the other, and so you see that. I mean, there could be finer quantities. Maybe things do not look so perfect, but there could be extreme values like. You see, I mean, here, the various plots are for different pressures at inverse temperatures beta equal to 1. I mean, so of course, maybe if you go to extreme values, so we don't know really, right? But I mean, at least for these parameters, you get very good agreement. So sorry for going over time. I mean, should have sort of talked less. And anyway, so thank you very much.
Thanks, Herbert, for this very interesting talk. So I'll first see if there are any questions from the Zoom. Okay.
Good.
Is there any question from the audience here? Yes.
No, what is the question? Sorry, what does the plot show? Ah, okay. So let's see this here. So let's look at this plot here, right? So first of all, here you see the parameters which I do. So the beta is, so the temperature is 2 in our units, and the pressure in our units is 0.3, right? Okay. So we have a system of 4,000 particles. And now what I'm computing here, so the 0, 0 means that this red curve is now the density correlation. So the point is that, so you see, I mean, okay. So let me just do the density. I mean, so I'm looking at the density which has the index 0 at the point xt, and then I'm looking at the correlation the same object 0 at origin at time t equals 0, and then I do the GGE average with beta and p, right? I mean, so these are inverse temperature and the pressure. Okay, so I'm looking at this particular correlation function. Okay, now the assertion is that initially, you know, it will be something which we don't really know, but if I wait not, you know, infinitely long, but sort of, you know, like 600 is, for instance, good, but, you know, if I would be able to do 10,000 time steps, presumably I would still see the same thing. The claim is that this object sort of, you know, has first a factor 1 over t in front, which comes because, you know, when I integrate over x, I mean, this somehow has to be conserved, and therefore, you know, I mean, I need it to have the correct value. And then there's sort of a function g, and that's simply a function of x over t. Right? And what is plotted in these pictures is that, you know, we first check that, you know, it really scales ballistically, and then we plot this function g here, right? So this is what we do, okay? And so this is why you see, so the factor 1 over t has been taken care of, and this is what you see over here. And so you know, this argument is, so to speak, the x argument. I mean, you know, this function, you know, has a cutoff because, you know, there's sort of like a maximal speed how this propagation, how these perturbations can propagate, right? So sort of like a sound speed. So you know, further out it will be just 0. Okay. Okay, and now okay, so that's this thing, and then we did here, you know, so we have the red curve, I mean the blue and the green curve. So the red one is density, the green one is momentum, and the two one is energy, and here we put the cross correlation. So forget about all the other things, right? Okay, and now okay, so now somewhat thickish lines over here. I mean, in color are the data from repeating, you know, doing molecular dynamics and repeating, you know, roughly, I don't know, 5 million times. Okay, and the dotted lines are the one from the theory, which, you know, I was able to explain you only one very small aspect. I mean, there are many other aspects which I cannot cover in such a talk, right? I mean, so I just explained to you this notion of generalized Gibbs ensembles, but there goes more into it, right? I mean, but anyway, I mean, you know, just emphasize again what I said, that you know, I mean, there's a numerical algorithm which is you know, by now we have good computer code, so this goes very rapidly, right? I mean, you know, you know, we have computer codes where this takes minutes or so, right? I mean, or even less, right? I mean, so we know how to do it. Basically, you have to solve some integral equations, and then you know, then okay. It's not. I'm not saying it. You know, you need a lot of knowledge, but you know, this is something which is available, right? If you do the molecular dynamics, of course, you know, if you average many times, then it just takes a long time, right?
I have one
Yes.
question. So from this exact solution in this model system, how much of the usual thermodynamics you get from the free energy? For example, the convexity of the free energy or the linear response.
Okay, that's.
Because you have the exact expression and.
Yeah, no. I mean okay. So I mean, you know, convexity because I'm working in sort of grand canonical prescriptions. I mean, you know, convexity just stays, right? I mean, because you know, I mean, it carries over. And what was the other question you wanted to cover?
The linear response.
The linear response. Yeah, you see. So okay. So maybe I didn't emphasize this. You see, you know, the density of states actually does come from a linear response computation, right? Because see, if you make a little perturbation of the confining potential, I mean, then this gives you. So okay. I mean, you know, maybe it's sort of not really proven up to the, you know, sort of a complete proof, but you know, I mean, I think that okay. So maybe I should say it in the following way. For the case of the total lattice, I mean, you know, where we did this sort of approximation that there's only interaction with the nearest particle in terms of label, right? There's a very beautiful work by Alice Goyennet and her student, and they prove all these things for the TODA, right? I mean, so for the Calogero, I mean, you know, the sort of, you know, I mean, it's too new and we haven't really done it, but in the case of TODA, I mean, you really, I mean, it's a very nice paper. I mean, this is and you know, I mean, she proves, you know, that in the limit you get this variation formula, and she also proves that when you do this linear response computation, then you get the density of states, and you know, the density of states sort of satisfies sort of kind of equations, you know, this Euler-Lagrange equation, such kind of things, right? I mean, so if one really wants to sort of have something where one actually has proved mathematical properties of these things, I mean, this is the paper to look at. However, there's one thing which is actually an interesting question, which is totally up in the air. You see what we do, I mean, also for the total lattice, but also in this case, what I tell you is a precise information about the distribution of the eigenvalues. Now you could ask yourself, I mean, okay, that's fine, but you know, it's a Gibbs state. What do you know about the spatial structures, the spatial statistics, right? And that's, of course, you know, from kind of experience with this and other systems, I mean, you would expect that you know, you should have sort of exponential decay of spatial correlations, but that's something that nobody has actually done. You know, it doesn't. I mean, of course, somehow you have to use this machinery, but it's another step that, you know, from having this kind of information on the eigenvalues, you actually produce information of, you know, what is the spatial statistic. I mean, yeah, I mean, qualitatively, you know, what is the spatial statistic in particular, but everybody in this community believes that, you know, you should have exponential decay. But that's something which I mean, nobody, I don't know how much people have worked on it, but at least what people tell me, you know, are really interested in the problem is that you know, there are sort of pieces which are missing, right? I mean, you okay.
Okay, thanks. Thanks again for the. Should I stop there?